Good morning. Today is February 25, Perspectives on Data Science. This is a lecture on variable selection. Before we start this lecture, do you guys have any questions on the project data files?
I had some questions yesterday. Hopefully they'll be sharing those with you.
Yeah, there are some people met in the office hours with me. So, so yeah.
Sharing what their concerns were and making sure that no one else has his concerns.
So data files are in different formats, which we shared you. If you got a Excel file or CSV file, you're lucky enough, but there are people who got .mat files and .h5 files. So what the people are doing, they're trying to convert it into what's the Excel sheets or CSV files. But the whole point behind that is you can use various data files or data types to open in Jupyter Notebook. So instead of trying to convert from one format to other formats, just try to open the same format in the Jupyter file. You can work with mat files as well in the Jupyter Notebook in the Python. So the whole point is just try to work with the same format we gave you. So don't just try to convert that into other formats. Okay.
I think the student I was talking to yesterday were basically trying that. It's not a model. They were trying to see if they can make it work.
Yeah, they try to change it to CSV format, but what that does, that just converted the first row instead of the entire data set. So in mat file, there are various files, so it's difficult to convert. So we need to work with data files, not to convert.
I think another student was talking about looking at their data set. They didn't know what they should use for the dependent variable. That's kind of the next step.
That's what they need to figure it out. That's what the project is about. Yep. Today we're going to start with variable selection. So variable selection is something which we select before we model. So we just don't want to build a model with all the inputs, like clubbing all the inputs and forming a model. So we just need to select some of the features which are relevant to our model, and then and then build the model. So instead of taking the entire subset of all the input variables, we are just going to select a few. So we're going to see how to select those variables while building our model. So we have different methods, but the basic idea for selecting the variables are the subject matter expert. So there are some people who know better than the models about the data set they are using. For example, if someone is trying to solve a clinical data classification or detecting a disease from the data set they have, so there are some people out there who know better than the models. So first consult the subject matter experts and ask them which variables should I include in the model, or which variables will mostly contribute to the classification or clustering they are going to do, and then try to use these methods. These methods will try to give us the features which are needed to build our model, but it's not like a thumb rule. Okay, so this is just to give us an idea of which variables are contributing most to the model building. Okay, it's not like only use these variables. It's not like that, but it gives us a basic idea. So this is where we are. Today we're going to discuss about variable selection. So we have finished all of these things, and we still need to discuss about data visualization. So that's we're going to do on Wednesday and Thursday's lecture. So we are going to use various visualization tools, such as what are we going to use for the data visualization? Uh, Power BI. So, yeah. So we just encourage you to bring your laptops to the next lecture to do the visualizations along with us. So that's going to be a lab lecture instead of a lecture. It's a lab. So try to bring your laptops and do the work simultaneously. So there will be some submissions in the class as well. If possible, we'll try to submit everyone a file at the end of the lecture. So today we are at variable selection. So what is variable selection? As discussed, it is a process of selecting a subset of relevant features or variables from the total features in a data set to build a machine learning algorithm. So there are some methods to select a subset of features that mostly contribute to the model building. So we need to select those variables, and to select those variables, we have some methods. So we named it as variable selection. So advantages of selecting a variable: improved accuracy, correct? So if we include all the variables in our model we will not be having more accuracy, because there are some features which do not contribute to our target variable. So if we include such features, our accuracy will be decreased. So it will improve our accuracy. Simple models are easier to interpret. So instead of including all the independent variables, if we include only few of the variables, it's very easy to interpret, like which variable is contributing most, or what's the weights for each of the variables. So it's very easy to interpret instead of including every variable in the model. So shorter training times, yes, we'll have shorter training times because we have less variables. So we have shorter training times. Enhanced generalization by reducing overfitting. So you guys know what's overfitting and underfitting. So if we include all the variables, it may lead to overfitting sometimes. So easier to interpret by software developers. That's again a repeated point. Reduced risk of data errors by model use. Variable redundancy, bad learning behavior in high dimensional space. Yes. So if we have more features, so it will be in higher dimensions. So it's always bad behavior in higher dimensional space, bad learning behavior. Okay. So the whole point here is to reduce the independent variables and try to build a model instead of including all the variables into the model, okay, so that we can reduce the dimensions. Feature selection techniques. We have three feature selection techniques discussing in this lecture or in this class. So now we're going to discuss about filter methods and wrapper methods. In the next lecture, we're going to discuss about embedded methods. So the next lecture is going to be on Monday and Tuesday, because we're going to discuss about data visualization Wednesday and Thursday. So filter methods. So the name itself says, what's a filter method? So we're trying to filter out the variables before building a model. We're trying to filter out the variables using various techniques or various scores or statistical methods. So that's called a filter method. So the idea here is to filter out the variables before building our model, not like selecting the variables. We're filtering out the variables. Okay. So it's generally used as a pre-processing step. So filter methods are used sometimes before we build our model. So before we build our model, we'll try to do EDA, exploratory data analysis, and we'll get to know which are the significant variables, and we will try to use those variables in our model. Okay, so that's something done before building a model. So that's a pre-processing step. Okay, so it's not like building a model, but it's a pre-processing step where we need to consider which variables are significant to our model building. Feature selection is independent of any machine learning algorithm. Yes, so since we are doing it as a pre-processing step, so it's independent of the model we are trying to build or the target we are trying to achieve. Features are selected based on their scores, statistical scores in specific, yes, in various statistical tests for their correlation with the outcome variable. So not just correlation, we have various statistical tests to do before we build our model. So based on those test scores, we are going to select which variables are significant for the model building. Okay. So these methods rely on the characteristics of the data. So feature characteristics do not use machine learning algorithms. Yes, we do apply filter methods before we build our model. So tend to be less computationally expensive. Since we are filtering out some of the variables, it's less computationally expensive. So we don't need to build our model with all the existing features. Instead, we select few of the features, which again reduces risk of computations on our systems as well. Yeah. Usually gives lower prediction performance than wrapper methods. So you are going to get to know about this method later on. Are very well suited for a quick screen and removal of irrelevant features. Yes, filtering means removal of irrelevant features. So it's easy to use, or it's easy to remove irrelevant features using filter methods. So filter methods, we're going to discuss about basic methods, univariate feature selection, information gain, Fisher score, ANOVA F value for feature selection, correlation matrix with heat map. I guess you are well aware of all these terms. So you know about F score. So how is it significant with the interval levels? And correlation matrix, you know how to build a correlation matrix with heat map. We're going to select the variables which are highly correlated. This is one of the statistical feature as well. We'll select F values with lower F values. And we also have a Fisher score, and which you're going to see now. So basic methods. So remove constant and quasi-constant features. So constant features, like if in a data set, if both the variables are trying to tell the same thing, so that's like constant features, like same values on both the rows, something like that. So show constant features show the same value for all the observations of a data set. So data frame contains column with all rows the same. So it's not like duplicating, but it's like it's something both are trying to tell the same thing. So including both of those in the model to predict is not a good idea, because both of them are trying to say the same thing. So that's called a constant feature. So they provide no information for machine learning model to discriminate or predict a target. So quasi-constant features show the same value for the great majority of the observations of the data set. So this is something, again, a constant feature, but it's not like telling the same thing, but it's up to some level. It's trying to say the same thing up to some level. So you know your data set better, so you will be knowing which features are trying to explain your predicting variable. So you will be knowing like which two variables are trying to say the same thing, or which two variables are mostly trying to say the same thing. So that's about the constant features. So we'll try to reduce the features if both of them are trying to say the same thing. We'll include just one feature instead of including both the features, because that's like correlation between those two will be one or something like that. So variance threshold from sklearn is a simple baseline approach to feature selection. It removes all the features with covariance doesn't meet a threshold. So default threshold is 0, removes constant features. So same values in all samples. So this is something which is trying to see the correlation. If the correlation is 1, so it's the score given is 0, and it removes that constant features. Or we can set the threshold to remove. Like if it's above 95 correlated between both of the variables. If we are trying, like if we think of removing the variables above 95 correlated, one of the variables, so you can do that. You can change the threshold value here. And univariate selection methods selects the best features based on univariate statistical tests like ANOVA, sort of a pre-processing test. Methods are based on F scores, estimates the degree of linear dependency between two random variables, assume a linear relationship between the feature and the target, assumes that the variable follows the Gaussian distribution. So univariate selection is nothing but we are trying to select only one feature for one target variable. So it's simple. Any test you take, whichever the variable is getting the highest test or the best test, we'll take that variable to predict our y variable. Okay, so that's sort of a pre-processing test. So methods are based on F test, or if we have F score less than, or which is less than the other variable, we consider that variable, or that's the degree of linearly dependency as well. So assumes a linear relationship between the feature and the target, and this tries to follow a normal distribution. So which we discussed in the assumptions of linear regression as well. So this is one of the assumption for linear regression, that's normal distribution. So this tries to assumes that the variable follows a Gaussian distribution or a normal distribution. Okay. So univariate feature selection. So selects k best, removes all but the highest k scoring feature. So we have different matrices to select a relevant feature. So we have various statistical methods. So we'll try to include a variable with best statistical score. Okay, so select k best. So higher the k score is better the feature. So we select the highest k score. We'll select the highest percentile if we are trying to see the variables in percentiles. So removes all, but it uses specified highest scoring percentile of features. or generic univariate select. So performs univariate feature selection with a configurable strategy. So if we try to give our own algorithm or configurable strategy, it will try to remove all the features except the best performed. So this allows us to select the best univariate strategy, select FPR, select FDR, select FWE, so etc. So you can refer this scikit-learn website as well as a reference material. If I try to open this, let's see what's inside there.
It's a virus.
Okay. So the basic idea is univariate feature selection. We have only one variable, one y variable. One x variable. So we try to get the best predict best variable that predicts the y. Okay. So based on the statistical scores we decide, or based on the algorithms we have predefined, and so on. Next. Some methods take the scoring functions as input. So this is trying to explain about various different methods like optional p-values, default f classification, and we have divided the statistical tests for classification tasks and regression tasks as well. Classification is something which is trying to classify the things, classify the output, or classify the y variable into different categories such as medium, low, or high, or anything. And regression is something which we are trying to predict, so which we are going to see how it performs in the future. So that's F regression, mutual info regression, and so on. So mutual information methods can capture any kind of statistical dependencies. Non-parametric requires more samples for accurate estimation. As that's information gain. So this is a measure how much information the presence or absence of a feature contributes to making the correct prediction on the target. So information gain. So this is a technique that helps to know if a, a particular variable, or if how a particular variable performs on a dependent variable, if it is included or excluded from the model. So this algorithm tries to see including the model in the prediction and excluding that variable in the model prediction, and tries to see the difference and tells us and gives us a score. So that's called information gain. So mutual information measures the information that X and Y shares. So it measures how much knowing one of these variables reduces uncertainty about the others. So this is something like uncertainty quantification, or yeah, that's a probabilistic methods. If X and Y are independent, then knowing X gives no information about Y. Yeah, so if the both are not depending on each other, so knowing one variable does not give any information on the other, and that's the opposite if both are dependent on each other. So in real world, there is no variables that are independent to each other. Okay, so there are no two variables that are zero correlated in real world. So if we try to perform the statistical tests, there will be no variables that has zero correlation. So there is some correlation between any of the variables that we take in real world. So if x is deterministic function of y and vice versa, so if x determines y or y determines x, then knowing x determines the value of y. Okay, so thus the mutual information is the same as the uncertainty contained in y alone. Okay, so that's again there is some links to Wikipedia where you can go and look up what is there. Yeah. Mutual info classification. So it determines the mutual information for the discrete target variable. So mutual information between two random variables is a non-negative value, which measures the dependency between the variables. It is equal to 0 if and only if two random variables are independent, and higher value means higher dependency. So we'll see what are the statistical tests we can perform to determine the score. So this function relies on non-parametric methods based on entropy estimation from k nearest neighbor distance. So k nearest neighbors, if you are not aware of what knn is, you are going to see in the later lectures, but it's something for now you can understand. Like if we have two variables, and if we have third variable, we'll measure the distance between these variables and get to know which one is dear, and we'll classify it to that subset. So that's something knn, k nearest neighbors, will define the value of k. So it can be used for univariate feature selection. So coming to regression, So mutual information for a continuous target variable. So if it's classification, it's discrete. If it's regression, it's continuous. That's the only difference, because in classification, we'll try to classify the things. So that should be discrete one. So which you have seen in the graphs when we explained. And when it comes to regression, it's a straight line, or whether it's a parabola or anything. So that's basically a continuous variable, which we are trying to predict. So that's the only difference. Mutual information between two random variables is a non-negative value, which measures the dependency between the variables. It is equal. If it is equal to 0, then the two random variables are independent, and higher values means higher dependency. Okay. The function relies on non-parametric methods based on entropy estimation from KNN neighbors. So it can be used for univariate feature selections. So Fisher score, chi-square implementation. So chi-square implementation is a scikit-learn. It computes chi-square stats between each non-negative features in class. The score should be used to evaluate categorical variables in a classification task. It compares the observed distribution of the different classes of Y among the different categories of the features against the expected distribution of the target class and regardless of the feature selection. So chi-square values is a score, is a statistical score which you can get using the Python code. And what this score tells, or the score explains, is about the categorical variable. So it tells how much. Again, it's all the same test. So everything tries to explain about the dependency between X and Y variables. So it's important to know what the score tells us, and it's important to know how to interpret that score on the variables we have and try to select those variables. That's the bottom line behind these slides. So we have various statistical tests which we have discussed here, and there are a few which we haven't discussed as well. So you need to know what those scores are telling. You need to know whether both are dependent, if the statistical score is high or low, and you need to select the features based on those statistical values. So if you need to know behind the math, you can very well do it on your own, because this course won't. It's not a math course, so it's the programming course. So we just program things, get the scores, and we'll try to see if they are dependent on each other or not. But behind those codes, we have math. If you are interested, you can search on your own. So ANOVA F values. So it provide for the provided sample. If the features are categorical, calculate a chi-square value. So chi-square are calculated for categorical variables. If the features are quantitative, compute ANOVA F score. So that's the basic difference between chi-square statistics and ANOVA F score. So we compute chi-square statistics for categorical and ANOVA F score for quantitative, the numericals. So the F score determines if when we group the numerical features by the target vector, the means of each group are significantly different. So F score is something like calculating the means between each of these groups and trying to explain the significance of Y variable with respect to X. So correlation matrix with heat map. I guess you know what's the correlation. So we will consider the variables with highly correlated. So high correlation means it is trying to explain something about Y variable. So it has some relationship between the Y variable. So it's highest correlation means highest dependency. So it's not like positive or negative correlation. So we have high correlation in both positive and negative. So most people confuse here. They think like high negative correlation means no correlation. It's not like that. Both positive, highly positive and highly negative correlation are depending on each other, but in the opposite directions. That's it. So both are dependent, highly dependent on each other. Okay, so there's nothing to do with sign here, positive or negative. It's just indicating the direction of the line. Okay, so correlation is a measure of the linear relationship of two or more variables. Through correlation, we can predict one variable from other. Good variables are highly correlated with the target. Correlated predictor variables provide redundant information. Variables should be correlated with the target, but uncorrelated among themselves. That's another important point we need to consider. As we discussed earlier, if both of the features are telling the same thing, so that including both of those variables to predict our model will not be beneficial or decrease our accuracy of the model. So correlation should be between y and x variables, not between x1 and x2 variables. So if both are highly correlated, both the x variables are highly correlated, it's highly encouraged to remove one of the variables. But again, before these tests, we need to consult our subject matter expert. So there is some person who know more about this data set. So we need to consult them before removing anything from the code. So the bottom line, if the subject matter expert says that's a important variable and the correlation is not that much, we are decided to remove that variable. Just don't remove that. Just keep it in your model. And if the subject matter expert says it's not important, you can remove it, but our model is showing highly correlated, then keep that variable. There is no point of removing that. So just keep it. So the subject matter expert believes it's not important, but the model believes it's important. So just keep the variable in the model. Okay. So correlation feature selection evaluates subsets of features on the basis of following hypothesis. Good feature subsets contain features highly correlated with the target, uncorrelated to each other. So that's what we discussed in the entire filter methods. So any questions on filter methods? So filter method is something which we are going to do in the pre-processing steps. So it's not like about the depend on model. So it's independent of model building, but it's something which we are going to see the statistical tests or EDA on the variables and try to see which variables are important for the model building. So that's about the filter methods. Okay. So no questions. Okay. So wrapper methods. So this is another type of variable selection. So in wrapper methods, we try to use a subset of features and train the models using them. So until now, the filter methods are a pre-processing step, but the wrapper methods are something which are used when we are trying to build our model. So when we are trying to build our model, we try to evaluate the model based on various features that we selected as the independent variables and try to get the output, the accuracies of the output and try to decide which features perform better on the model. So that's everything about our wrapper methods. So we take a subset of features or we take some features, we try to evaluate on the model we built. We compare with other features as well and try to see which model performed well on the given data set. Okay. So in wrapper methods, we try to use a subset of features and train the model using them. Based on the interfaces that we draw from the previous model, we decide to add or remove features on the subset. That's what we discussed. Now the problem is essentially reduced to search problem. So if you are aware of the programming, so this is something it's something related to search problem. So if we are trying to search a number that's less than 10, we're trying to have if x equal to 10 or if x less than 10, we'll give that variable to our list. If it's not, we'll remove that. So that's something what the wrapper method is doing. So it's trying to predict, it's trying to build the model and it's getting its accuracies or the mean squared errors or whatever the statistic it is, and it is comparing with the other set of variables, and whichever is highest, we're including it. So that's something which is similar to the search algorithm. So that's the same algorithm we are trying to use here, but in a different way. These methods are usually computationally very expensive because we are trying to build the model using various variables. So we are trying to use the subset of variables and we're trying to build the model number of times to see the best model performance. So this is computationally expensive because we are trying to build the model again and again. So the filter methods are computationally inexpensive because we are trying to eliminate it and trying to build it. So it's computationally inexpensive. It's trying to remove the features and make our model run. But here we are trying to build the model again and again with various subset of features, which might be computationally expensive. Okay. Wrapper methods, we have forward selection, backward elimination, exhaustive feature selection, recursive feature elimination with cross validation. So here are some terms which you are aware of. So cross validation, we have discussed it in the previous lectures. So it's something like testing the model using various features. Cross validation we have seen in the validation dataset, we're trying to validate using various subsets of the training values and try to predict the accuracies of our model. So it helps us to overcome the underfitting and overfitting problems to our validation data sets. So you know about this term, and it's the straightforward terms: forward selection, backward elimination. So we are selecting it in forward and we're eliminating it in backwards. That's it. So let's see each and everything in detail. Forward selection. Forward step selection or forward selection is the variable selection method which begins with the model that contains no variables, then starts adding the most significant variables one after another until a pre-specified stopping rule is reached or until all the variables under consideration are included in the model. So we'll try to perform some kind of statistical tests to our model or to our variables. It tries to, so we'll take a null set. So there are no features included in that set. Then we'll try to include the features which scores highest or which are significant. And we'll try to include one by one in the forward manner. We'll try to check and we'll try to, if suppose, for example, if we are trying to get all the variables which are significant at 95% interval. So that's something like p less than 0.05. So if we are trying to make statistical test on the variables, and if we are trying to include the variables that are less than the p values are less than 0.05, then we'll start one by one and start adding it into our null subset. Or we can have a stopping criteria. If the null set is filled like 3 variables, we'll stop the criteria then. So that's something forward selection. So we have null subset and we'll take the variables and include in our subset. That's it. So it begins, then starts adding, then stops when the criteria met. That's simple. And determines the most significant variable. So what are the variables that are included in the subset? So those variables should have more significant, should be more significant. Yeah. The more significant variable can be chosen so that when added to the model, it has smallest p value or provides the highest increase in r square values. So the r square is a statistical test that reduces the distance between predicted and the actual values. So we'll just try to get those values and we'll just try to square those values, because some are negative and some are positive. Because if the error is in upward direction, it's positive. If the error is in downward direction, it's negative. It doesn't mean like the negative has less direction. It doesn't make sense, right? So we'll just square those to get it positive and we'll square root that. So that's something r square. And it provides the highest drop in model RSS, residual sum of squares. So residuals again are errors, the distance between predicted and actual, compared to other predictors under consideration. Yeah. So choosing a stopping rule. So it's up to us to choose a stopping rule, but the stopping rule is satisfied when all remaining variables to consider has a p-value larger than some specified threshold if added to the model. So the model tries to check if the p-value is less than 0.05, and it tries to add the variables into the subset. And if all the variables that are not added obviously has greater than 0.05. So that's something a stopping point. If all the variables that needs to be selected are greater than 0.05, so that's a stopping point. The algorithm stops over there and tries to build a model that we have selected the variables into the null set. So when we reach this state, this will terminate and return the model that only contains variables with p-values less than the given threshold. So how to determine the threshold? So how to determine the threshold, that again depends on you, because it's your data set. You know more about your data set than anyone else. So you need to know what's the statistic you need to consider as a stopping point or as a threshold, basically. So it's something like if it's a clinical data set, then we need to be more careful while building the models. So then the p value should be very less. Or if we are trying to build a gaming data set, like if we are trying to predict how a player performs based on the given set of variables, then it's not like that much important in real world, because clinical data set should be important because the people matters lives, right? So lives matter. So we need to consider more while doing the clinical data set. So but if you're doing something like gaming or something, it's okay to go here and there, like p-value less than 0.06 or 0.09 or something like that. This clinical data set somewhere, now the accuracies of the clinical data set are also above 99%. So you need to be like taking the p-values less than 0.01 or something like that, which are more dependent on each other. So that again, selecting the threshold entirely depends on your data set, because you know more about your data set. So it's a fixed value, so determined by AIC and BIC. So it's information criteria, AKK information criteria, and Bayesian information criteria. So I guess most of you are aware of what the Bayesian is all about, the Bayesian probabilities. So if both are depending on each other, so A depends on B, we have a formula to calculate the probability of how much it explains the Y. So or how much probability we have in getting that variable, okay. So if we let AIC and BIC automatically determine the threshold, it will be different for each variable. So let's see what AIC and BIC is. So Akaike and Bayesian. So these are two terms, addresses model selection. They are not the same. So before Bayesian information criteria, so we only used to have Akaike information criteria because most of the time the scientists were not accepting this Bayesian information criteria until the late 90s, somewhere like that. So we the BIC came into the picture after 90s. So before that we just used AIC, but now we are including BIC in our statistical methods as well, because it's giving us more better probabilities in predicting Y variables. Okay, so for example, if you take a clinical data set again, so it's not like determining whether a patient is having a disease or not. So if a model tries to say if the patient is having a disease, it should be able to say how much probability it has for the patient to have the disease. So that's why again Bayesian neural networks coming into the picture in determining these things, because it's just not trying to classify the things into having a disease or not, but it is also trying to explain how much probability he has in determining a disease if the patient has. Okay, so these are the formulas. These are some of the formulas which you can know about AIC and BIC. So AIC versus BIC. So generally tries to find unknown models that has high dimensional reality. This means the models are not true models. In AIC, this comes across only true models. So not consistent. It could overfit. It could underfit. Derived from frequentist probability, derived from Bayesian probability. Have we missed something? When comparing the Bayesian information criterion AIC, penalty for additional parameters is more on BIC than AIC. Yes. So if we are considering Bayesian information criteria, so the whole point is if we are trying to add a new variable to our existing model, it tries to penalize it. It tries to see how much deduction in accuracy we have. So BIC penalizes more when compared to AIC. So BIC will reduce more score when compared to AIC when we add a variable to an existing model. Okay, so that's why BIC here it could underfit and it could overfit here. So that's the basic idea behind this point, how it could overfit and underfit. Okay. So backward elimination, again, that's the second method. Backward step selection or backward elimination. So we'll try to eliminate the least significant features. So before this, we added the most significant features to our null set, but now we'll consider a set with all the features, and we will try to eliminate the features which are less significant. So that's the opposite direction we are doing now. Okay. So begins with a model that contains all variables, starts removing the least significant until a predefined stopping rule is reached or until no variable is left in the model. So that's the same thing we discussed earlier, but in the opposite direction. So we selected the significant features and added to our null set. That's the forward selection. And now we are taking all the variables and removing the least significance. So that's the backward step selection. Determine the least significant variable. So again, that's the opposite what we have discussed. If we are trying to include a variable that has least p-value in the forward selection, now we are trying to remove a value that has a highest p-score in the backward elimination. So that's the basic difference between these two. Rest all doing the same. Highest p-value in the model, or it elimination from the model causes the lowest drop in R squares, and it eliminates from the model causes the lowest increase in RSS compared to other predictors. So that's the opposite points we have discussed till now. Forward step versus backward step. Forward step selection, when the number of variables under consideration is very large, even larger than the sample size. So favor small models, fewer variables. If we have fewer variables, then it could be easy for us to get a forward step selection. But it's computationally expensive to include all the variables and trying to eliminate one by one. So instead of doing that, if we have many variables, we'll just do backward step selection. We'll select the most significant variables. If we have less, we could do it. We could consider adding the variables by checking one by one. So favors large number of variables. Unless the number of candidate variables greater than sample size, use a backward step approach. Or both of the best worlds, we could use both forward and backward selection as well in the same algorithm we use to get the best model. So notes on stepwise selection. So stepwise selection provides a reproducible and objective way to reduce the number of predictors compared to manually choosing variables based on expert opinion, which more often than we would like to admit, it biases towards previous one's own hypothesis. So again, a subject matter expert's opinion matters because he know more than the model. So he know which features contribute to the prediction of this model more than the model itself. Okay, so we need to consider the subject matter expert's opinion as well. Note, however, automated variable selection is not meant to replace expert opinion. In fact, important variables judged by background knowledge should still be entered in the model, even they are statistically non-significant, which we have already discussed. The automated variable selection is most helpful in the exploratory data analysis, EDA, especially when working on new problems not already studied by other researchers. So this is most useful when there is no subject matter expert in the field. So if you are trying to solve a new problem in your research, then it's always better to have pre-processing steps or filter methods and wrapper methods to be used to select the variables, because no one knows about the data set, and it's always better to let the model choose its own variables and get to know which variables are mostly significant to the problem statement. Advantages of stepwise selection. Again, it's easy to apply. It improves model generalization. It yields a simple model that is easy to interpret because we have less variables, so it's easy to interpret. It's objective. It is objective and reproducible. Limitations of stepwise selection. It does not consider all possible combination of potential predictors. So until now, we are not trying to build a model and not trying to compare the models. It's just trying to predict a model accuracy based on the input variables. It's actually not considering a subset of variables and using it to build a model and comparing the accuracies or the errors between these two variables. But it's just doing considering all the possible outcomes. It's not considering all the possible outcomes. It's just considering the variables that needs to be included in the input. Okay? It produces an unstable selection of variables. It does not consider the causal relationship between variables. So it does not see whether both of the independent variables are depending more on each other or not. It just tries to see which are more dependent on y variable. It does not check which two variables are highly correlated in the input variables. Okay? So those are some of the limitations. So limitations to stepwise selection. So it outputs biased regression coefficients, confidence intervals, p-values, and R-square. So regression coefficients will appear larger, will appear narrower, will appear larger R-square values, p-values will appear smaller, also invalid. So these are some of the limitations for stepwise selection. Exhaustive feature selection. So in an exhaustive feature selection, the best subset of features is selected over all the possible feature subsets by optimizing a specified performance metrics for the certain machine learning algorithm. For example, if the classifier is the logistic regression and the dataset contains 4 features, the algorithm will evaluate all the 15 features combinations as follows. That's the limitation we have discussed now. So what's the limitation we have discussed? The forward or backward step selection or elimination is not considering the output of a model and not trying to predict or not trying to check the accuracies between two model performances. That's what the exhaustive feature selection is doing. If we have um, four independent variables, it's trying to check on each of the variables by building the model and checking the accuracies. So that's the basic idea. So all the possible combination of one features, if we have 4 features, and all the combinations of 2 features, again all the combinations of 3 features, and all the 4 features included, and it tries to see which uh, performed better, which model performed better, and it tries to include those variables as our final model prediction. But the problem here, it's more computationally expensive. We're trying to build multiple times our model, so our CPU may die in between building the models, so on. So we generally won't consider this method, but it's always better to know we have these type of algorithms as well in checking all the subset of features and calculating the model accuracies and keeping the independent variables that performed better. Okay. Yeah, that selects one results that best performed. Example, classification accuracy. And this is another greedy algorithm as it evaluates all possible feature combinations. It is quite computationally expensive, and sometimes it features space. If feature space is big, even unfeasible. Okay, so if we have a lot of, it's okay to have 4 independent variables. We can easily test our models by performing 4 different models or performing the subset, so that will be 2 power 4, I guess. But if we have a large subset of features, so trying to check for all the combinations, which is nearly impossible to check all the combinations. So in real world, if we are trying to predict anything which has the independent variables of 90 or 85 or 80, so it's actually not possible to check that with these greedy algorithms. Let's see, recursive feature elimination. So performs a greedy search again to find the best performing feature subset. It iteratively creates models and determines the best of the worst performing features, and at each iteration it constructs the subsequent model. So it's basically the opposite. Instead of doing it for 1 and 2 or 3 and so on, it does the opposite one. It eliminates the model that does not perform better, or it tries on different subsets and it checks which feature is performing worst while predicting the y, and it removes that thing from the subset and it tries to do all the other 3 combinations. So it is something works like this. So it's your algorithm, so you have multiple ways to build it. So it's basically the idea of how the greedy algorithm works. So it's again computationally expensive as well. So in the worst case, if the dataset contains n number of features, it will do a greedy search for 2n combinations of features. So it because it eliminates features in the coming iterations. So recursive feature elimination with cross validation again. So with cross validation, it's a technique that selects the best subset of features for the eliminator by removing 0 to n features iteratively using recursive feature elimination. So it tries to eliminate one feature and check the model, and again it includes that feature and eliminates other one and checks the model performance and so on until all the criteria was met, and it removes the feature that hasn't performed better. So that's the cross validation. That's the idea behind cross validation, and we are implementing it with recursive feature selection or elimination. It selects the best subset based on the accuracy or cross validation scores of ROC, AUC of the model. And for further exploration, you can go ahead and look at these um, links. So there are some libraries which are preferable other than the one we have discussed. We have Polar and so on. So we have many open sources where we can go ahead and explore the things. If you are trying to learn the math behind each of these statistical tests, there are some resources out there where we could learn. Um, it's not up to this class, but it's useful if you are trying to have your career in data science. It's always better to know the math behind that. So instead of getting like what is r square, we need to have more r square, or we need to have less p value. But how are they computed? So we are running the code and it's giving a value, but how is it computed on the behind the scenes? So if you are interested, you can learn the math behind that. It's not complicated, so it's easy enough to learn the statistics behind this data science. And yes, we highly encourage you to learn as well, because if you are trying to have your career in data science. Any questions?
Yeah, so one of the things that we discussed yesterday was that pandas versus polars.
I don't know about polars.
Yeah, polars, no. I'm going to share what that is. That is a brand new product, open source. Of course, all the stuff the Python community is open source. And it's a competitor of pandas. And yesterday in class, I mentioned this. It just came out like last fall, is when I first learned about it. Another student just learned about it the day before class yesterday. He was like, probably really excited. He says, "Can I get extra credit for using polars?" I said, maybe. Anyhow, if you look at that, it really excites you. The great thing about open source is there's always options, different things you can use. The bad thing about open source is there's always options. There's different things you can use. And there's more than one way to do it. And it gets more complicated. Polars intends to be a more intuitive replacement for pandas. Whether it is or not, I don't know. I haven't had a chance to evaluate. If someone's curious enough, possibly one of you was working with a data set that's a simple come and separate values file, so you don't have to worry about from your data. Or maybe there's something already in there, or it works with mat files better. So it's a thing that you can look at if someone's interested and wants to share that information. We'd be very interested to hear what you find out about it. Again, we also pointed out the what was it? The graphics package.
GUI.
Yeah. Scrolling, there you go. And we'd already seen, for sklearn is ML extend. And if you're doing graphics, there's matplot based on matplotlib, and there's the Seaborn library for doing graphics. They're both similar ways, but slightly different. Some are more intuitive to some people than others. So be aware of all those options that you have, especially if you go forward into data science. We've got the recommended tools in this class. We're trying to pay attention, keep the recommendations to ones that are best for now, but at the same time, 2 years from now, even 6 months from now, there could be something new that comes along that just blows away the stuff that we're using in this class. So,
Yep.
Yeah.
Mm-hmm.
That was that.
And I'll stop recording. You guys have any questions in this lecture?